You've seen little bits of JavaScript code, and in this section, I want to talk about what connects that world to the machine code in the CPU. So this will be on generally the topic of computer languages. So a programmer works in some computer language, and computer languages are said to have high-level features. And that means things like loops and if statements and strings. Those are facilities that are more complicated than what's present in the really simple machine code on the CPU. So the programmer writes what is called source code in whatever computer language they're writing. So here is an example of some C++ source code. This assigns a string into a variable and then puts an exclamation mark on the end of that string. You'll notice it looks kind of similar to the JavaScript code we've seen. A lot of these languages at the syntactic level, they're kind of similar with the use of quotes and semicolons and whatnot. So how do you get from the C++ source code, say, to running on the CPU? So one strategy uses what's called a compiler. And the compiler is a separate program. And what the compiler does is it looks at all of the source code and it does a bulk translation over to create a big body of machine code. So for example, maybe there's a part of the source code where there's an if statement. And there's not a specific instruction in the machine code for an if statement, but maybe there's a sequence of 5 machine code instructions that in effect make up an if statement. And so the compiler does that kind of expansion. So just as an example, Firefox is written in C++. And so to make a new version of Firefox, someone runs the C++ compiler and it reads in the many source files, the great body of source code that makes up Firefox, and produces essentially firefox.exe. Firefox.exe is the output of the compiler to just translate all of that source code. A couple things to point out about this. The compilation only has to happen once. So there's somebody's source code, someone makes firefox.exe, and then you can just send out firefox.exe. The end users don't need the source code, and they don't need the compiler. So the compilation can just sort of be done at the factory, in effect. Another feature of this is that it doesn't work backwards. So I can distribute firefox.exe, all this machine code, but there's not something that will read that in and go backwards to give me a big body of source code, or at least not perfectly. You can sort of do it imperfectly, but ideally, to produce a new version, you really want the source code. So let's talk about the source code a little bit. So if you want to add a feature or fix a bug to Firefox, really the way to do that is to go back to the original source code and rework it, just as we've done in JavaScript. So add a few lines or an if statement to change some behavior in some way in the source code, and then run the compiler again to make, in effect, a new version of Firefox that has this little change that you've put in the source code. Just since we're talking about source code, this also gives you a good sense of what open source software means. So open source software is a format where the program is distributed, but also there's access to the original source code to the program. And usually this comes with a license saying, hey, here's the source code. If you want to make your own version or fix a bug or whatever, this program, feel free. So the two main features of open source software is one, it's typically distributed for free, so it's just cheap. But the other feature is that it comes with a sort of freedom, because if the software is closed source and you want some different feature, there's some bug that you need implemented, you're really dependent on the vendor who holds the source code. Like, well, do they feel like implementing that feature? In contrast with open source software, it's like there's no handcuffs. The source code's available, and if there's something that you really wanted to do, or say the original vendor goes out of business, then because you've got the source code, you could, maybe pay someone to make a change and produce your own custom version. And so it comes with this sort of deep, you can think of it as an insurance policy. So often there's many different types of license terms for open source software, but most often they require in some cases that if you take the source code and add some feature, that you then offer those changes back to the community. So sort of in the same way that you've benefited from others' work, they can benefit from your work. In the details of how that can be done is complicated. There's many different forms of it. I'm going to talk about open source software a little bit later on, but I just wanted to mention it now because it really gets at this idea of what is the source code of a program versus just having the .exe of something. So thus far I've just talked about C++. So there's a whole nother very big category of languages, which I'm going to call dynamic languages, or sometimes interpreter languages. And this is sort of a big tent strategy. There are many different languages with many different qualities, and I'm just going to sort of lump them into this large category. So examples of dynamic languages currently are Java and JavaScript and Python. So one way that these can work is that they're implemented by what is called an interpreter, as opposed to the compiler case I was describing earlier. So an interpreter is a program which takes in code written in some language and sort of quote-unquote runs it. So the best example is that there's this computer language called JavaScript that actually we've been using. And web browsers, which are programs, include as part of them a JavaScript interpreter. And so when the web browser comes across a page with some JavaScript code in it, it can use the interpreter to run that code to make it do whatever it's going to do. So at a very high level of detail, the way an interpreter works is that it deals with the program one line at a time. So here's a little bit of JavaScript code. If the interpreter wanted to run this, well, it would look at the first line, and it would look at what that line says, and then the interpreter would do it. So in this case, the interpreter would say, oh, well, I guess I need a variable named a, and I need to put a 1 in it. So once it's done with that line, then it goes ahead, and it does the next line, and so on. So the compiler does this big bulk translation from the source code into machine code, but it's not really running the code. It's just doing a translation to be run in the future. In contrast, the interpreter really lives in the moment, just going through the code line by line and just doing it. So let me talk a little bit about the differences between these two. And I should say as a disclaimer, there are many computer languages. There is no best language. The old joke is that really, when you're in the seminar and you're arguing about the pros and cons of something, ultimately the answer is just, it depends. Like there's not a best language. It's like, well, what's the best language for this situation with all the features? So broadly speaking, compiled code does tend to run faster. When you compile C++ code and produce that exe, it's sort of, in a sense, lean. A lot of detail and decisions has been stripped out as much as possible. On the other hand, dynamic or interpreter languages tend to have more features that make the programmer's job a little bit easier. Or put another way, broadly speaking, programmers can tend to get more work done per hour in dynamic languages than they do in compiled languages. However, there's no free lunch. It is also the case that dynamic language code tends to run slower on the CPU in terms of just getting work done compared to a compiled language, compiled source code that was going to do the same thing. So an example of this, a great example of this, is memory management. So memory management refers to the problem in the code of knowing how many bytes are needed to store something, and in particular for how long. Well, I need these bytes for here on line 6, but maybe on line 20, I don't need them anymore, and I could reuse those bytes for something else. And it's actually kind of a complicated problem. In C and C++, memory management is, to a degree, manual. And that just means that the programmer, they're producing all these lines of code to do stuff, and there's going to be times when they may have to add some lines or do some thinking to help guide the memory management. So there's some programmer effort required. In contrast, most dynamic languages have what's called automatic memory management. And this means that no programmer input is required. That the lower on the stack, that the language is going to notice automatically when memory is needed, when memory is not needed anymore, it can be recycled, and just take on that whole problem. So this fits within the trend of dynamic languages I was mentioning earlier. So this is an example of how, well, because the programmer just has less to do, they're able to just get stuff done a little quicker. So memory management is a great example of that. However, you can also imagine this is one of the things that makes dynamic language code run a little slower, because the CPU now has this additional bookkeeping problem where it's looking at memory and trying to figure out when it can be reused. So very broadly speaking, the trend for computer programming today is towards dynamic languages. That the trade-off that the programmer will get things done a little quicker at the expense of using a little more CPU or maybe a little more memory, that's a pretty attractive trade-off for many problems. And this is maybe a little unintuitive, but you can think of, well, what's the scarce quality for a computer program? And oftentimes it's the programmer, that having skilled programmers working on a problem who are working on this working in this domain, a lot of times they're hard to find, and so using up their hours, using as fewer of their hours, looks attractive. In contrast, the CPU, we want programs to run as fast as possible, but CPUs are fairly inexpensive and fairly effective. And there's even this funny effect where Moore's law keeps making it more true, where the CPU, in effect, each year gets a little bit cheaper. But if you think of the balance between the programmer cost and the CPU cost of getting something done, that means in terms of the share of the pie, the programmer is in effect getting more expensive each year, a little bit more scarce. So these fit into the pattern that, on the whole, dynamic languages are becoming a little bit more popular. Just a last thing I'll mention is that there's a thing called a JIT, a just-in-time compiler. And this is sort of the natural synthesis of the compiler and interpreter strategies of trying to get the best of both worlds. It's like, well, we'd like to have a dynamic language with all these features, all these programmer-friendly features, but we want it to run fast. And so the JIT will take parts of the code and try and compile them on the fly. And so it tries to sort of marry the two approaches. It turns out this works pretty well. So all modern browsers now have JITs for JavaScript code. So actually, when you were running JavaScript code, even for this class, inside of the browser, there was a JIT that was, in a very sophisticated way, on the fly, taking those scraps of JavaScript code and compiling them on the fly into native code. Anyway, you do not get exactly the performance of compiled code, but it gets fairly close. And so this is actually how most dynamic languages work first. And I'll say, well, it's an active area of research, but it seems to work pretty well.